Stanford University.
Okay, tonight we're going to do a number of things. We're going to talk about uncertainty. We're going to talk more about the Schrodinger equation, the various versions of the Schrodinger equation. We're going to talk about how things evolve with time. We've talked about that some already. Let's see what else we have here. Yeah, we're going to apply the Schrodinger equation idea for the evolution of systems to our favorite little system of one spin. But then if we have time, and I hope we will, I would like to move past the single spin. We have a general theory of quantum mechanics for which I announced what the basic rules were and the basic principles. Hermitian operators are observables, vectors are states, and so forth and so on. Orthogonal vectors mean distinguishable. A very, very general set of principles. And so far, we've applied it to exactly one simple system, the simplest possible system in the world. We're not finished with it yet. But hopefully, tonight or next time, we will move on to the next simplest. Well, no. It's the next to next simplest system. There's a simpler one in between, but two spins. Two spins is the next to next simplest system. Why do you think that two spins are the next to next simplest system as opposed to the next to simplest? A spin has two states. How many states do two spins have? Two orthogonal states, four. So what happened to the state with three states, the system with three states? You can imagine a system with only three states. That's the next to simplest. So two spins is the next to simplest. But let's get on. First of all, the concept of uncertainty. I'm not going to do the mathematical uncertainty principle tonight, but we should just talk a little bit about the fact that there are observables, pairs of observables, which cannot simultaneously be measured. The basic principle is that if you measure something, then by the definition of a good measurement, you leave the system with the same value that you measured. Otherwise, you couldn't confirm in the next round of, you couldn't confirm what you had measured. So it's important that you leave the system, at least momentarily or instantaneously, having the same value that you measured. The measurable quantities of a system are the eigenvalues of the observable operators, the operators that represent observables, and the states in which the observables are definite, in other words, in which there's no ambiguity about them. The thing that you get after you've done a measurement of a certain quantity is an eigenvector, or the eigenvectors of the observables. Now, supposing we had two observables which could be simultaneously measured. If you measure, you can measure one, and it will leave it in a state with that same value, but you can also measure two things simultaneously. It doesn't matter, it could be one after the other, but let's just call it simultaneously. You make two measurements simultaneously of two different things, and you leave both of them in eigenvectors of the quantities that were measured. Two distinct quantities. That must mean that the states that you leave things in are simultaneous eigenvectors of the two distinct things. If you can measure things simultaneously, it means basically that they have the same eigenvectors, or that there exists a complete set, a basis of, incidentally, the term, somebody pointed out to me that the term basis, that I've been misusing it a little bit, and that's probably true. I use the term basis to mean a complete set of orthonormal vectors, meaning to say they're all orthogonal. Quantum physicists tend to use it that way. I think in mathematics, the notion of a basis does not require the vectors to be orthogonal. It just requires them to be linearly independent. All right, that's not a big deal. I just pointed out to you. I will use the term basis to mean a complete set of orthogonal normalized vectors. The eigenvectors of an observable can be made to be a complete orthonormal basis. When I say they can be made to be, I mean you do have the ambiguity. What happens if there are two eigenvalues with exactly the same value? All right, then you have an ambiguity as to how to choose the eigenvectors, but you can choose them perpendicular. And if you have two distinct operators which can be simultaneously measured and therefore simultaneously left in eigenvectors of those quantities, it must mean that there is a basis of vectors which are simultaneous eigenvectors of both quantities. In other words, there exists a basis if, let's call the two observables L and M. These are Hermitian operators, L and M, and it means that if L and M are to be simultaneously measurable, it must mean that there's a complete basis of states which are both simultaneously eigenvectors of L and eigenvectors of M. So that must mean that L on I equals, let's use the notation for eigenvalues of L. Let's use the notation little L sub I. That's, instead of lambda, L sub I times I. That's the condition that I be an eigenvector of L with eigenvalue L sub I. And at the same time, the same set of states must be eigenvectors of the M observable. And so this must be true for a complete set of states. Now, let's apply L and M in sequence. First L, then M. And then try it the other way and see what we get. So, first let's start with L on I. Here we have it. But now let's take M, multiply it by L, and then hit the eigenvector I. Well, from the first relationship here, this is equal to M times L sub I times I, right? All I've done is plug in this first equation. But now L sub I, that's just a number. That's a number. That's not even a matrix. It's just a good old number, an eigenvalue. And that means we can write it as L sub I M times I. But we now know that M times I is just little m. So what does this give? This gives L sub I M sub I times I, the product. Okay, that's not so surprising. I is a thing which can be measured, M and L are things which can both be measured simultaneously. And if we multiply the two of them together as matrices or as operators, they become another observable whose eigenvalues are just the products. Good. But if we did it exactly in the opposite order, Lm on I, we would get exactly the same thing. The order, these are just numbers, and so that the order that you write them down doesn't matter. L sub I times M sub I is the same as M sub I times L sub I. And so this is equal to the same thing. Same thing. Now supposing you have two operators which have exactly the same action on every member of a basis. That means they will have the same action on any superposition of vectors formed out of a superposition of the basis vectors. In other words, they will have the same action on any vector. M times L and L times M have exactly the same action on any vector, and therefore M times L is equal to L times M as operators. All right, so we've proved the following theorem, that if two things are simultaneously measurable, the two observables or the two operators representing those observables commute. L times m and m times L are the same, or L times m minus m times L, which is the commutator, L commutator m, must be equal to 0. You can prove a stronger form of this theorem, and it just goes the other way. If you have two operators, I'll leave this to you. If you have two operators which commute, remember, if you have two operators which commute, it means that you can find a complete basis of states in which both of them simultaneously, in which the complete basis of states are simultaneous eigenvectors of the two operators. So it goes both ways. Given that you have two things which can simultaneously be measured, it follows that they commute. And if two things commute, it follows that they can be simultaneously measured. They have a complete set of common eigenvectors. All right, so the condition then for things to be simultaneously measurable is that they commute. What if they don't commute? In fact, we already have some examples of things that don't commute. Sigma x and sigma y and sigma z, no two of them commute. No two of them commute with each other, and therefore they do not have simultaneous eigenvectors. And that's no surprise. We know that the eigenvectors of sigma z are up and down, the eigenvectors of sigma x are left and right, and they're not the same thing. They're different. They don't lie, they're not proportional to each other. So there are examples of operators which don't commute. In fact, we're going to work out the commutation relations for them. They don't commute. In fact, they don't commute. And that's an indication that you can't measure them simultaneously. That's the idea of uncertainty. The idea of uncertainty is when you have two objects, two observables, each of which you could decide to measure, and get an answer. You may not know what the answer is going to be. It's statistical, but you can measure them. After you've measured them, be certain you can repeat the measurement and find consistency, each of them, but not both of them. Okay? In classical physics, there's no such thing. If you can measure A and you can measure B, then you can measure both A and B. And you can be certain about both of them if you can be certain about either of them. All right, so that's just, and we'll come back to that theme of uncertainty and quantify it. There may be states where, although you're not certain, well, all right, we'll come back to it. We'll come back to it. We want a quantitative measure of the necessary degree of uncertainty in measuring two things simultaneously, and that is the uncertainty principle. But for the moment, we have the idea or an explanation of why there are uncertainty between observables in the first place. Yeah.
Could you repeat that? Why you have two observables that they have to share a common orthogonal basis?
Well, if you measure them and you get answers for both of them, you have to leave the system in a state which is an eigenvector of either one of them, both of them. That's the rule. When you measure something, it leaves it in a state of definite thatness, whatever that happens to be, which means an eigenvector. If you measure two things if you can measure two things simultaneously, it must mean the state that you leave it in is an eigenvector of both of them. Okay. All right, let's come back now to the evolution of systems. As I said last time, I went back and looked at the classical mechanics notes, and I realized, and I said, okay, I have something like about 50 pages of quantum notes. The equivalent classically was how many pages in the classical mechanics? It was about a quarter of a page, I think. Just a statement that states are sets of things and that you can write on a blackboard, points on All right, so 50 pages to get to where classical mechanics we were after about 30 seconds when we were, and that's just the way it is. The next thing we did when we talked about classical mechanics was we talked about how states change with time. That took another page, arrows going from one to the next and so forth. Here it's not so bad. It's not going to take us another 50 pages, fortunately. In fact, we've already laid it out. It took basically, I would say something like about 5 pages or something in my notes, I think. 4 or 5 pages, maybe a little more. So we're beginning to compress, and things are, once you got the idea of states, then the next is a little bit easier. Okay, so let's remind ourselves what we said about the time evolution. The Schrödinger equation. The Schrödinger equation is the equation that governs the time evolution of systems. We began with the idea of the conservation of distinctions, or conservation of distinguishability of states. The implication was that states which are orthogonal remain orthogonal. It was easy to prove from that, and I hope you've proved it. You should be able to prove it, that the U operator, I should have brought my own pens. The U operator, remember what the U operator is? If you want to know what a state is at a later time from its value at time 0, this stands for time 0, then you apply a certain operation. It's more than just an operation, it's a linear operator. Okay? A linear operator U, and you get psi at time t. U, of course, is a function of t. The later or the earlier that you want to project the vector forward, you put in different t's here, and that was the basic equation. But then we required another ingredient, and the other ingredient is that orthogonal states stay orthogonal. So, for example, if we have 2 orthogonal states, let's call them for the moment I and j instead of psi. I and j are orthogonal. In fact, I and j might be members of an orthonormal basis. Right? Let's take them to be members of an orthonormal basis. And then you allow I to evolve for a time, and you allow j to evolve for a time. The ket vector I becomes u, let's say u of t, times I. If you start with I, after a time it's u of t of I. J evolves with the Hermitian conjugate of u, j. And the assumption is that if I and j were orthonormal, u times I and u star times j are also orthonormal. So the way to say this is if ji is equal to a Kronecker delta, then this is also equal to a Kronecker delta. In other words, putting u and u dagger, sandwiching them between orthonormal bases here, does not change the inner product. And from that you can conclude, since this is true for any members of the basis, that u dagger u is just a unit operator. We did this last time, I know. The unit operator. It does nothing. Okay? U dagger times u. Then we went another step. We said, all right, let's consider the evolution from time 0 to an infinitesimally short time later. So we're interested in, let's call it u of epsilon, where epsilon is a small time. And we argued, well, first of all, if epsilon is 0, nothing happens. To say that nothing happens means that u is the unit operator. All right, so u of 0 is just a unit operator. It does nothing, just leaves the state the same. We added one more thing, and that was a kind of continuity. I may not have spelled it out. A kind of continuity, and that was that u of a small time is close to the identity. In other words, in a very small period of time, the state doesn't change much. So that's the same as saying that u is equal to the unit operator plus something small of order epsilon. And I used my freedom of definitions, just choosing definitions, to write this as minus I epsilon times h. There was no content in that minus I epsilon. I can just absorb it into h. I put it there. In fact, had I really wanted to keep track of all the interesting constants, I would have put an h bar over here. But this is all a matter of convention. Whether or not we include an h bar, whether or not we include an I, whether or not we include an epsilon, is just simply a definition of how to of h. We could have called this whole thing k, and then said k is equal to I epsilon over h. You know what I mean. I don't have to say it more. All right, let's take away the h bar. I'm going to forget it anyway. It's units. It's simply units. And then we fed this. Oh, let's write the other one. U dagger of epsilon is equal to 1 plus I epsilon h dagger. Dagger meaning Hermitian conjugate. Then we fed these two into the unitarity condition. And what did we find? We found that h minus h dagger must be equal to 0. That's what happens if you feed these two into the unitarity condition, or another way to say it is h is equal to h dagger, or h is Hermitian. Now, that's big news. Why is that big news? It means that h is an observable. It's something that we can measure, and we should be interested in it. What is it? And of course, the answer is, it's the not of course, but as I said last time, it is essentially, it is, apart from a factor of Planck's constant, it is the Hamiltonian. What's it got to do with the classical Hamiltonian? We talked about it a little bit. I'll come back to it. But for the moment, it's just called the quantum mechanical Hamiltonian. It's a thing which in some way or another, well, in a very clear way, generates time evolution. Incidentally, you might think that this, all right, well, let's go on. We went a little bit, another step. We say, okay, let's write the equation. Psi of epsilon, now this is pure review, psi of epsilon is equal to psi of 0 minus I epsilon h psi of 0. I just plugged in for what u is, and then transposed this to the left-hand side and divided by epsilon. Transposing to the left-hand side makes this minus and puts an equal sign here, and then divide by epsilon. This is the obvious thing to do. And what do we get on the left? We get the time derivative of the state vector of the system. The time derivative of the state vector of the system, d psi by dt is equal to minus I h psi. So what h is it's a rule for how you update the state of a system. If you know it at an instant of time, then at the next instant of time, you make an incremental change in the state of the system proportional to I minus I h times psi. It's a little machine for telling you how to update the state of the system. Now, it sounds awfully deterministic. It sounds awfully much like classical determinism. Classical determinism is also a set of rules for updating the state of a system. So in what sense are things not deterministic if you know how to change the state from one instant of time to another? Well, they're not deterministic in the sense that even if you know the state of a system, you simply don't know the results of every measurement. The knowledge of the state of a system in quantum mechanics is not equivalent to the knowledge of the outcome of every experiment. What does it tell you, the state of the system? It tells you probabilities. So this is basically a rule for updating probabilities. It's not a rule for updating knowledge, complete knowledge of the state of the set of experiments that you could do. All right. But in some sense or another, the state vector evolves. I don't want to call it deterministically, because deterministically carries baggage with it, but it evolves in a known and definite way. Now this is true, but only if you don't interfere with the system. In classical mechanics, you can interfere with the system arbitrarily gently and not cause any changes in the way it's evolving. In quantum mechanics, when you make a measurement, you necessarily disturb the system. So this is the evolution of the system of an undisturbed system that is not in the process of being measured. Yeah.
So what if the system happens to be in an eigenstate of the measurement you're going to make?
It's all right. So what?
Then you would not disturb the system.
Well, that's a special case. Yeah, you're right. You're right. That's right. If you're in a special case of an eigenstate of the system and you measure it, it doesn't disturb it. So, right. So that is an exception to what I said. But generally speaking, the generic situation is when you measure something, you disturb something else about the system. Okay. This equation is the Schrodinger equation. Now, it's sometimes called the generalized Schrodinger equation. The actual Schrodinger equation, as Schrodinger wrote it down, was for a particular kind of system, the motion of a particle. But it has exactly this form. This first became known as the generalized Schrodinger equation, and then people dropped the generalized. We now think of this as the form of the Schrodinger equation. And what it is it's an equation which tells us how states change with time. It can be applied to the simplest system of a single spin. It can be applied to the second simplest and the third simplest system, and to systems of arbitrary complexity. But this is the form that it has. All right. That's where we more or less were last time. Okay, so let's erase everything but the Schrodinger equation. Actually, this is called the time-dependent Schrodinger equation. The time-dependent Schrodinger equation is an equation for how things change with time. There's also another equation which is called the time-independent Schrodinger equation. H is an observable. It corresponds to the Hamiltonian, but Hamiltonian is nothing but energy, at least in classical mechanics. So one might expect that H is the operator that's representing the observable energy of a system. Okay, now, we're going to make a measurement of the energy of some system. How do we do it? Let's not worry about that. There's one way we could do it. We use E equals mc squared, and then we weigh the system carefully, really, really carefully, and in that way determine its mass and its energy. Okay? That's not a very efficient way to do it, because the change of the energy of a system when you heat it up or something is so negligible that, but that's one way. There are many ways to measure energy. But what are the possible outcomes of the measurement of the energy of a system? That, of course, depends on the system. It's not something you can answer in general, but depending on the system. For example, if you measure the energies of an atom, you get one of a denumerable family of possible answers, namely the energy levels of the atom. If you measure the energies of a harmonic oscillator, again, you get a denumerable collection of possible answers. If you measure the energy of a particle moving in a non-closed orbit, then, in fact, you get a continuous possible family of possible answers. So the question of what the energies are depends on the system, and it depends on the choice. Of course, it's not a choice. You know, the systems have Hamiltonians. It's not up to you to dictate to a system what its Hamiltonian is. It may be up to you to try to discover what its Hamiltonian is, but let's use the terminology. You get to choose the Hamiltonian, meaning to say you get to study different possibilities. And depending on the choice of operator that you put here, that you call H, you can get different energy levels. How do you how do you calculate and determine what the possible outcomes of the energy measurement are? You use the statement that the values that the energy can take on are the eigenvalues of the Hamiltonian, like any other observable. So you write another equation, H on. Let's call it the ith. Now, I now represents an eigenstate of the energy. It doesn't represent any old basis. It represents, in particular, the, in fact, maybe we should indicate that by writing in here the energy, the ith possible energy level, H on E sub I, is equal to the eigenvalue E sub I times the eigenvector associated with that energy. The notation of putting E sub I inside the ket vector just means nothing more than this is the ket vector, which happens to be the eigenvector of H with eigenvalue E sub I. And how many such E sub I's are there? Well, there's a complete basis of them. Whatever the dimensionality of the system is, whatever the dimensionality of the space of states is, there's that many eigenvectors of the energy. And your job as a physicist is to try to find them. So that's the time-independent Schrödinger equation. Next thing we did, again, a lot of review tonight. Next thing we did was talk about the evolution, time evolution of expectation values, average values. Okay. I complained bitterly about the terminology expectation values, all right, but many, many years ago I gave up on this, and so it's become expectation value, but it really should be average. It's okay, I'm okay with expectation value. I'll use but it really should be average. Okay. And here's what we found. Well, what we said is the thing that changes with time is the state vector. So we're interested in calculating psi of t. Remember the expectation value. I'll just remind you, the expectation value you get by sandwiching the observable in a sandwich between the bra version of the state vector and the ket version of it. We proved this. We proved that this is the same as the average, the statistical average. And I won't go back over that now. This is the average value of L, the observable L. And we can ask how it changes with time. It changes with time because psi changes with time. And here we know how psi changes with time. There's two factors of psi here. So when we go to differentiate this with respect to time, there will be two terms, one coming from differentiating this and one coming from differentiating that. If you remember that when you flip from bra to ket, you have to complex conjugate, and that complex conjugating changes the sign of I, you will come to the conclusion that this is equal to, now I always get the sign wrong. Let me try to get the sign right. I think it's minus I times LH minus HL, average value of that, psi. We worked that out. We used that L on psi gives you H on psi. That's this piece over here. And we used that L, when it acts to the left, gives you a term with H acting to the left with a minus sign. Okay, so here's what we find then. We find that the time derivative of the average of L let's just write it this way. d by dt of the average of L, I'll use that notation for the average of L, as a function of time is equal to minus I times the average of the commutator of L with the Hamiltonian. If you know what the Hamiltonian is as an operator or as a matrix, and you know what L is as an operator or a matrix, you can compute the commutator. And when you've computed the commutator, you can compute its average value. Just use this rule, the sandwich rule. Let's call it the sandwich rule. And it tells you the right-hand side tells you what the left-hand side, how it changes with time. Do you find it odd that there's an I there? Well, I did the first time I saw this. First time I saw this, I said, wait a minute. The time derivative of a real thing can't be imaginary. We're going to find out that commutators of real things are always imaginary. So the imaginary will go away. We're going to do some examples, and you'll see this is not hard to prove, but we'll do it by example. Sometimes this is written in a shorthand. The shorthand is just that dl dt is equal to minus I times the commutator of L with H. But at least at this stage of our knowledge, what this means is that it should always be sandwiched and thought of as an equation for the average values of things. And so there we have what are called the Heisenberg equations of motion of a system. That brings us to the study of commutators. The study of commutators, and I want to go through that just again a little bit. Commutators have some rules associated with them. The rules are very, very reminiscent of the rules for Poisson brackets. So go back and read about Poisson brackets. I'll write down what the rules are. The general rules, algebraic rules of Poisson brackets and commutators. And then we'll just check. Are they really true for both of them? Well, the rules for Poisson brackets we did last quarter. Poisson brackets are written this way. Okay, A, B. And I'm not going to write out how you express them in terms of the P's and Q's of classical mechanics. But there was a few simple rules associated with them. First of all, there were some linearity rules. That if you add two operators, if you add two things and then take the Poisson bracket with a third, they add and so forth. This is certainly true of commutators. But there was a couple of non-trivial rules. Well, first of all, the Poisson bracket is odd, which means that when you interchange the two entries, it changes sign. Minus BA. That was one property. This is certainly shared by the commutator. If you interchange L and H, you interchange these two terms and you change the sign of the commutator. So that's true of the commutator also. If A and B are now quantum variables, this is also equal to minus B times A. There's really only one important relationship, and it's the product rule. The product of A and B Poissoned with C. The operation of Poissonning. If you remember, the Poisson bracket was a combination of derivatives. Derivatives of various things. If you go and use that definition of the Poisson bracket, use the rule for derivatives of products, what you'll find out is that this is equal to, this is the Poisson bracket side, it's equal to A times the Poisson bracket of B with C plus the Poisson bracket of B with C times, sorry, Poisson bracket of A with C times B. Now, the order that you write down A and the Poisson bracket, that's not important. These are just numbers. I mean, these are just ordinary functions or numbers, and it doesn't matter which order you multiply them. But I wrote them in an order which I know that the commutator will also satisfy. Operators, the order does matter. So I wrote these in a specific order. Namely, I put A on the left over here, and then I put B on the right over here. Maybe it's not too surprising. A appears on the left in this factor, and B appears on the right, so I kept the order intact. Okay, let's see if this is true for commutators. What would it say? It would say, well, let's write it out. A times commutator BC, sorry, go back. It would say that commutator of AB with C is equal to, we'll put a question mark here, I don't know if it's equal to yet, A times the commutator of B with C plus A with C, A with C times B. Let's check if that's true. This is very easy to do. We don't have to do any derivatives. All we have to do is write out the meaning of this. Commutator of AB with C is the same as AB times C minus C times AB. Everybody see why? First you put AB on the left times C, and then you put C on the left and AB on the right. And you take the difference. Definition of the commutator. Let's see what we get on the right-hand side. On the right-hand side, we get A times BC minus CB. That's this term. And then from here, we get plus AC minus CA times B. These are operators now, and in this calculation, they're operators. The order matters. Okay, let's see what we have. We have ABC. Here's ABC. That's good. We have, all right, so this is a friend. We have minus CAB. That's this one over here, CAB. That's also a friend. Our enemies are ACB, but they occur both the same way. ABC, no, ACB. That's a bad one. But here we have also ACB. One with a minus sign, one with a plus sign. So it's ACB minus ACB, and we're finished. The commutator satisfies the same algebraic rule as the Poisson bracket. Is this an accident? No, of course it's not an accident, but we'll get to the deeper reason for it eventually. Which comes first and which is more basic? Certainly the commutator is more basic. Quantum mechanics is more basic than classical mechanics. Classical mechanics is an approximation to quantum mechanics. So it stands to reason there ought to be a classical approximation to the notion of commutator, and there is. That leads us to speculate, if you like, but I'll take it as not a speculation. I'll take it as something that we'll discover or we'll be able to prove later. That when we go from quantum mechanics to classical mechanics, the Poisson bracket, let's see, the Poisson bracket becomes, I think, minus I. Now this equality doesn't quite make sense. This is something classical on the right-hand side. Maybe we should put arrows there. Commutator, A with B.
In that last equation that you wrote there, it seems, the bottom one, it seems like the right side is twice what the left side is.
Well, I don't think so. A, B, C, A, B, C. C, A, B CAB with a minus sign. And then we have a couple of extra terms. The extra terms are minus ACB plus ACB. Yeah, okay, good. You're allowed to make mistakes. It's good, slow me down. Yeah, yeah, all right. Now, nothing in what I've done so far tells you that this should be identified exactly with that. It might be identified with this times a numerical multiple. The Poisson bracket might be 7 times a commutator or a quarter of the commutator, and they would all still make sense. In fact, there's a dimensional difference between these. Poisson brackets are derivatives of A with respect to X, derivatives of B with respect to P. They have units which are different than just AB. The difference of units is actually soaked up in Planck's constant. If we work with Planck's constant equal to 1, then Poisson brackets are just minus I times commutators, but for dimensional reasons, there's an h bar there. Let's write it another way. Let's put the h bar on the left-hand side. Certainly, classically, we think of commutators as very small. In fact, we think of them as essentially 0, AB minus BA. So in the classical limit, the commutator is something which is just 0. How does that happen? Well, it's the h bar here. When h bar is very, very small, in units in which h bar is very, very small, which are just ordinary units. I mean, units like meters, seconds, kilograms. H bar is an incredibly small number, some 10 to the minus 30, I forget. It's a very small number. So in the classical approximation, commutators are negligibly small. But when keeping track of real quantum mechanics, the commutator is not 0. Okay, so that's the meaning or the notion of commutator. And the nice property now is that this relationship here is simply the quantum analog of an equation that we studied last quarter, dl by dt is equal to the Poisson bracket of L with the Hamiltonian. Which matches quite well with this. That is the essential reason at this stage for identifying H with the Hamiltonian. Classical mechanics, when packaged in this fishy way called Poisson formulation, the fishy Poisson formulation encapsulates, organizes everything into relations involving Poisson brackets, and in particular it says that the L by dt, L could be anything. Incidentally, L here is not the angular momentum, it's anything. The L by dt is equal to the Poisson bracket of L with H, and in quantum mechanics, in the sense of average value, we found that the L by dt is minus I times the commutator. So that's the essence of the connection between the Hamiltonian of classical mechanics and the quantum mechanics. Yeah.
One more time, this stage of the game, what's the definition of L?
Of what?
Definition of L.
L is any observable. Any observable. I used L for linear operator, but of course it should be Hermitian linear operator, so I might have used H, but then I would have gotten caught and found that H... Oh, H is Hermitian, and so is L. But I used L for a generic observable. So assume that L is Hermitian. Originally, I used it for linear. But now I'm using it to mean linear and Hermitian. All right, L could be H. L could be H. Right? We could study the equation of motion of how H changes with time, or better yet, how the average of H changes with time. Let's do so. Here we are. The H by dt is equal to minus I times the commutator of h with h. But the commutator of anything with itself is 0. And so, incidentally, is the Poisson bracket of anything with itself. Because Poisson brackets are odd, they change sign when you interchange the two objects. That means the Poisson bracket of a thing with itself is 0. So from a classical point of view, we could have derived the conservation of energy from the principle that the time derivative of the energy is the Poisson bracket of the energy with itself. Here we find in quantum mechanics a very simple thing, it's a similar thing. The time derivative of the, again, the Hamiltonian, is the Poisson bracket, is the commutator of the Hamiltonian with itself, and is therefore 0. Energy is conserved in quantum mechanics, or at least the average of the energy is conserved. Now, it's better than that. There's a very definite sense in which the energy is exactly conserved. But not for tonight. Mm-hmm.
In the introductory example there, we were talking about two operators.
Mm-hmm.
Is the physical example of that simply two particles with spin states?
Two what?
Two objects or particles with spin states?
If we had two spins, yeah, absolutely. Absolutely. In fact, whenever we build a system out of two systems, in general, the observables for one of the systems and the observable for the other systems commute with each other. That's why you can measure the position of me and Sanjay simultaneously, because because our positions commute. And so do our spins, but I think that's the question. That is the question you were asking? Yeah, okay, right. Yeah, but we haven't come yet. That's where I was going to go later, but I don't know if we'll get to it, to the question of composing systems, taking systems and making bigger systems out of composing them. And that would bring us to the issue of entanglement. I have a feeling we probably won't quite get there, but maybe we'll at least partly get there. All right, the next thing we want to do is solve Schrodinger's equation. I don't mean the one for the eigenvalues and the eigenvectors. That we solve by standard methods of, if we happen to know what the Hamiltonian is, and in particular if we happen to know it in some matrix form, then we're just calculating the eigenvectors and eigenvalues of some matrix. Let's suppose that's done. We have the eigenvectors, we have the eigenvalues. Let's now find the general solution of Schrodinger's equation. In other words, how things evolve with time. You know, I realize that all of this is abstract, that the only system that we have to apply this all to is the world's simplest system again, and that's not very much. So at this stage, you're probably saying to yourself, when are we going to be thinking about real things, objects, systems? We will. We will, by all means. But I think having all of this apparatus, this abstract formulation of quantum mechanics will make it very easy and quick to start applying it to lots of things. Yeah.
Yeah. Do we know what H is for this spin system yet?
Well, okay, so all right, let me answer that right now. That depends on what we do with a spin. If we have a spin in free space, far from anything else, then its energy or its Hamiltonian is just basically 0. Incidentally, adding a constant to a Hamiltonian doesn't do anything. And the reason is because a constant commutes with everything. So apart from a possible additive constant in the energy, a spin which is not around anything else, it just doesn't, its Hamiltonian is 0, and that means that it doesn't change with time. If you put it in a magnetic field, if it happens to be a real spin of an electron, you put it in a magnetic field, the magnetic field induces a Hamiltonian, which I hope we'll get to tonight. and it causes the spin to do things, to have a time dependence. And then what the Hamiltonian would be would have to do with which direction the magnetic field was in. So Hamiltonians can be changed. I mean, you can change a Hamiltonian by changing the direction of a magnetic field. But I hope we get to this example tonight. But let's just first write down the general solution of the Schrodinger equation. To do that, we start by saying, let there be a basis of eigenvectors. I guess we called it, this is the same as E sub I. If I don't want to write E sub I, I will just write the ith eigenvector, but it means the eigenvector with energy E sub I. All right, we can take any state. Since I or E sub I are a basis of states, we can take any state. Let's call it A. Or should we call it psi? Let's see, what did I call it in my notes? No, I think I called it psi. I did. I called it psi. Psi. And let's think about psi at time 0. Well, no. Let's leave the time arbitrary. Psi is a sum over all of the eigenstates, or all the eigenvalues, of some set of coefficients, alpha sub I. I've used the term alpha in the past to denote the coefficients of states, of basis vectors. So any state, whatever, can be written as a superposition of eigenvectors of the energy, since the eigenvectors of a Hermitian operator are a complete basis. All right, so this is psi, and let's say at time t equals 0. Now, at time t, how does the state change with time? What's changing here? Well, the states I are just a fixed set of states. It's the alphas which change, the coefficients here which change with time. All right, so the coefficients in the expansion of an arbitrary state are typically time-dependent coefficients. That's what gives rise to a time dependence in expectation values and other things. Now let's write the Schrodinger equation. So we have psi dot, which we can now write. Let's take psi dot, d by dt of psi, d psi dt. That's equal, from here, sum on I, d alpha sub I of t with respect to t, times I. To differentiate the state, all we do is differentiate the individual coefficients. Now, Schrodinger's equation tells us to set that equal to minus I. Oh, different I. Holy smoke. Okay. J. Okay. Set that equal to minus I times H acting on this. But H can be brought in through the summation here, and this can just be written as summation over I, the coefficient numbers, summation over J, alpha j of t, H on J. Now what is H on J? Somebody said 0?
If the J's are constant.
No.
Oh, they're right.
Up there. I and E sub I are the same vectors. Go up to the top vector, to the top equation. H on the ith eigenvector is the energy E sub I on the ith eigenvector. Okay, so this just becomes E sub j. Here we have on the left-hand side a sum of basis vectors with coefficients alpha j. Sorry, where are we? Did I make a mistake here? Oh, sorry, this should have gone down here. This is wrong. Here. This should have gone down here. This is sum on j, d by dt of alpha j. And then, I'm lost.
Before the equal sign. That alpha and before the equal sign, that I should be.
Oh, yeah. This is correct up to here. This is correct up to here. Let's, okay. Yeah, right. Let's go back to here. And now let's calculate the, let's calculate the time derivative of this. What do? We put in minus I times h on j. Here is where I use h on j is equal to ej on j. Okay, I think that's what I had a moment ago anyway, isn't it? I think that's exactly what I had. Minus I, take out the minus I. All right, this thing and this thing are the same. So this sum must be exactly the same as this sum. If you have two sums of basis vectors, the coefficients must be the same. If you have two sets of basis vectors, if you have two linear superpositions of the same set of basis vectors and they're equal to each other, then the individual coefficients have to be equal to each other. So it follows that the alpha by dt is equal to minus I times the alpha j by dt, ej alpha j. All I've done is set the alpha dt equal to the coefficient in this equation over here. And that's the whole upshot. It tells you how the alphas change with time. For each j, this is a differential equation. Just to think of this as just a differential equation for alpha. What's the solution of this differential equation? We've done this kind of equation over and over again. The time derivative of something is proportional to the same thing, to the thing itself. Exponential solution, right? So the solution of this equation is alpha j equals alpha j at time 0 times e to the minus I ej t. If we differentiate alpha j with respect to t, it will bring down this factor minus I e sub j times the same thing. So we can now write the general solution of the Schrodinger equation. We've solved it for each individual eigenvector. This is the way the individual coefficients alpha change with time. But now we can go back. Let's go back to the original equation that the state vector is a sum over the eigenvectors. And let's plug in what we now know about alpha. We now have solved for alpha, and here we can write that the general state vector at time t, if you know it at time 0, let's suppose we know it at time 0. At time 0, it was just alpha j of time 0 times j. All that happens is each alpha j picks up a time dependence, and the time dependence is just governed by the energy of the state. Earthquake? All right, so all you do to find the general solution is you take the state, you break it up into eigenvectors of the Hamiltonian, and then whatever it was at time 0, the only thing that happens is the phase of each entry here changes with time with an e to the minus I times the energy of the state. Where would the h bar go in this formula? Anybody know? Underneath the I, or underneath the energy, or underneath the time, it doesn't matter, but it goes into the denominator here. This is the connection between energy and oscillations. Okay, this is the oscillations of the wave function, not oscillations of real things, but oscillations of the coefficients of the state vectors. While we're at it, let's do one more thing. Let's use our general solution of the Schrodinger equation to calculate how the average of L changes with time. We have an equation for it, but now we actually know how psi changes with time. And this is just a little bit of not gymnastics, just a little bit of fiddling around with equations. Some of you may recognize the equation we're about to get, but whether you recognize it or not, it's just explaining how the symbols are used, if you like. Okay, let's calculate, given that the state changes like so, let's ask how the expectation value of an arbitrary observable changes. What do you have to know how the average or the expectation value of L changes? L is some operator. I haven't told you what operator. Of course, you need to know what operator in order to say how it changes. Of course you do. But still, we can go a little ways. Let's plug in this formula for psi of t. This is sum of j, alpha sub j, e to the minus I, ej t times j. Now we have L, put L over here, and now we're going to do the same thing to this bra vector over here. But what happens when we do a bra vector? Let's do the bra vector. The bra vector is psi of t is summation, we better use a different summation variable, k, and then we will have alpha star sub k of 0. When you go from bras to kets, you have to complex conjugate. We'll also have to change this to e to the plus I e sub k t times the bra vector k. I've changed the summation index here so that I don't confuse it with this one. I've complex conjugated here, and flipped from kets to bras. All right, so I can put this over here, summation over k, alpha star k at time 0. This is at time 0. Times e to the plus I ekt. So it's a double sum. It's a double sum over k and j. That's not terribly illuminating, but let's just for fun, let's work it out. Now, what's the inner product of k with j? We see here the inner. Oh no, sorry, it's not the inner product of k with j. What we see here is L sandwiched between j and k. L sandwiched between j and k. The operator L acts on the state j, and then you project it onto k. Let's give that a name. Let's call that LKJ. That's exactly the kind of matrix elements we computed when we talked about the matrix representation of observables. The inner product of of L on J with K. That's what we called LKJ, just the matrix representation of the observable. And then we have alpha star K of 0, alpha J of 0. We'll talk about that in a moment. And then we have a phase e to the I, e sub k minus e sub j times t, summed over j and k. Now, the main reason I did this was just to illustrate the machinery. I did not do this because this is a formula of any importance right now, but some of you may nevertheless recognize it. It is Heisenberg's matrix formulation of quantum mechanics, Heisenberg's formulation of the way averages change with time. If you go back to Heisenberg's first paper on quantum mechanics, he guessed this formula, basically just guessed this formula. Every observable has two frequencies associated with it. That was weird. It was common for people to understand that an observable might be an oscillating observable. It might be something that oscillates and would have a frequency associated with it. But Heisenberg said there are two frequencies associated with every matrix element of an observable. This is where it came from. No, it came out of Heisenberg's head. But this is the way Dirac explained what, this is the way Dirac understood what Heisenberg was saying through this machinery. First, just the pieces. The pieces, this represents the observable, whatever the observable is. It's its matrix representation. These things have to do with the initial state, the state at time t equals 0. And these things here have to do with the way things change with time. Everything changes with time with two separate frequencies, and then you sum it all together, and that tells you how L changes with time, how the average of L changes with time. So we're putting together a bunch of machinery that we'll use. Are there any questions? Yeah.
Am I reading this correctly? Is it the case that the magnitude of the alphas stays the same over time?
The alphas are fixed. The alphas are just the alphas at time t equals 0, period. Yeah, yes, no, I think you're going back to here. Yeah, yes, that's correct. The magnitudes of the alphas stay fixed. It's the relative phases between them. So all of the time evolution has to do with these relative phases. Yeah.
So the Schrödinger equation is the partial derivative.
Is what?
The partial derivative with respect to time.
It actually doesn't matter. This just means the whole derivative with respect to time. It's usually written as a partial derivative, but it just means it could be written as a total derivative. Same thing. Psi only depends on time.
So
I mean,
psi will also function of same position.
it's not, well, yeah, that's okay. That's right. We will eventually come to think of psi as a function of time and position, and that's why it. But that's later. For the moment, it doesn't matter whether we use partial derivative or total derivative. It just means the change in psi in a small time, it doesn't matter whether yeah.
When you derive the time-dependent Schrödinger equation, you use the fact that the states stay orthogonal over time.
Mm-hmm.
I think that's an empirical fact.
Well, it is an empirical fact, but in fact, I think it's much more than that. The evidence that it's much more than that is also an empirical fact. And it's a curious empirical fact. People have tried to change quantum mechanics. And it seems to be as hard to change quantum mechanics as it is to change arithmetic or logic. if you start fooling around with it and try to change the rules, you very quickly find that something really bad happens. The probability is not conserved. Probability is not positive. Terrible non-localities happen where you can communicate at the infinite distances. And so quantum mechanics is not a thing which is easily changed. In fact, there is no known changes that can be made in it. Of course, there is one known change that can be made. You can just replace it by classical mechanics. That's a consistent theory. The reason it's a consistent theory is because it's a good limit of quantum mechanics. But there's no ways to change it, to deform it a little bit. My friend David Finkelstein, who is a very wise man, a great scientist, once explained to me that there are two kinds of revolutions in physics. He called one a plastic flow and the other a brittle cracking. What he meant by that, he considered, for example, general relativity to be a plastic flow. You can change it little bits. You can deform it a little bit. You can change Einstein's equations by changing variables. It's not something that you cannot change at all, and you can change it in little ways and deform it. Special relativity is very hard to change. Once you change special relativity, it's very brittle, and the whole structure of it goes down the drain. But nevertheless, you could change it a little bit. It's harder to change in general relativity. Most things go wrong, but quantum mechanics is absolutely brittle. And by that he meant not that the theory is in danger of being broken by anything, but that if you try to change it, you will get broken. So quantum mechanics is very hard to change. And I think the evidence for that is just all of the years over which people have tried to change it. Yeah.
So the E sub j and E sub k values, those are both real numbers, right?
Mm-hmm. Right.
So is the reason that we know that they're real numbers because the eigenstates that we chose are eigenstates of the H matrix?
Yeah. Yes. We derived from unitarity. Unitarity is this condition that u dagger u is equal to 1, or I, called unitarity. From that we derived that the Hamiltonian is Hermitian, and from that we can derive that its eigenvalues are real. Yeah. Mm-hmm. Of what?
Syntax.
Syntax.
At the top you have H bar with the ket vector E sub I equals E sub I. That first E sub I on the right-hand side of the equation is an eigenvalue?
No. Well, okay. This whole thing is an eigenvalue, eigenvector. But it's the eigenvector with eigenvalue E sub I. So you're labeling the eigenvectors by their eigenvalues. Mm-hmm. Here, it's just the eigenvalue.
That's what I'm looking
Right. And incidentally, this is a case where repeated indices do not get summed over. This is a case of the non-summation convention. Let's apply some of this apparatus to the problem of a single spin, a spin in a magnetic field. Let's see if we can calculate, in particular, how the average of the components of the spins change. As we do this, depending on your memory for classical physics, you may start to find some of it familiar. If not, I will remind you.
It's not as bad as fingers on the old black.
No, it's not. No. No, it is not. No, that wasn't terribly bad. It just reminds me of my cat. in the middle of the night. Okay, we have a single spin. Let's put the spin into a magnetic field. If we put the spin into a magnetic field along, let's take the z-axis. Let's be simple. Let's take the z-axis, put the spin in, put the magnetic field along the z-axis. A spin, in particular, the spin of a charged particle, is a little electromagnet. Charged particle spins around, and as it spins around, there are currents that flow, and it creates a little magnet. Put a magnet into a magnetic field, and you get an energy, and basically the energy is proportional to the misalignment of the magnetic field with the spin, with the axis of the spin. And the simple formula is that the energy is proportional to the dot product of the spin with the magnetic field. That's where we're going to start. We're going to start with an energy which is proportional. You have a magnetic field, and the magnetic field is along the z-axis. So what is the dot product of the spin with the magnetic field? It's going to be proportional to the z component of spin. The dot product of the spin with the magnetic field will be the component of the spin along the axis of the magnetic field. That's a guess, okay? Take that as a guess, which we could then study and then ask if the experiments on the spin agree with it. Okay, so we have a spin, we have a magnetic field along the z-axis, let's call it B sub z, and we have a spin, and the spin has components, sigma x, sigma y, and sigma z. People ask me, incidentally, why in the book that I'm writing about quantum mechanics there aren't more figures. There are lots of figures in the classical mechanics book. And the reason is very simple. I mean, it's a real reason. You can't draw quantum mechanical systems. Quantum mechanical systems are by their very nature not things that you can draw. If you try to draw them, you will always be trying to draw things which cannot simultaneously make sense. Okay? In particular, if I try to draw the components of the spin, I'll be trying to draw components of the spin which don't commute with each other, and it doesn't make sense to draw them. Nevertheless, there it is. Magnetic field and the spin, and we're just going to write now. We're going to take this as a guess, or as a postulate. The Hamiltonian is just going to be proportional to the component of spin along the z-axis times something proportional to the magnetic field. I'm not going to write out, it contains the electric charge, it contains a magnetic moment, it contains a magnetic field, but let's just call the coefficient here, let's call it omega over 2. That's a definition of omega, if you like. Whatever the right combination of magnetic field, charge, magnetic moment, in particular charge, magnetic moment and magnetic field, we'll lump them up and call it sigma over 2. Sorry, and call it omega over 2, and the reason for the omega will become clear shortly. Sorry, the reason for the 2, for both the omega and the 2 will become clear shortly. Okay, now what I want to calculate, I want to calculate the time derivative of the averages of all the components of the spin. Here we have the z component in the Hamiltonian, but I want to find out how all the components, sigma x, sigma y, and sigma z, how they vary with time. So in particular, I want to calculate the time derivative, dot for time derivative, of sigma x and sigma y and sigma z. Well, what is the rule? I'm afraid the rule has been erased, but I think you probably remember it. The time, and by definition now, this means the average of sigma x. I'm not going to bother writing the bracket, angular brackets there. We're now talking about the averages of sigma x, sigma y, and sigma z, and the time derivatives of the averages. All right, so if you remember, this is equal to minus I times the commutator of sigma x with the Hamiltonian, right? So the Hamiltonian is sigma z and we get another factor of omega over 2. Oh, yeah, that's correct. Likewise here, sigma y with sigma z times omega over 2, and likewise here, sigma z. Now one of these is very easy. Which is the easy one? The bottom one. Everything commutes with itself, right? Everything commutes with itself. So this is 0. And what does it tell us? It tells us that the component of the spin along the magnetic field, the average of it does not change with time. That also tells us, well, if we were doing classical physics, which we're not, if we were doing classical physics, it would tell us that the angle of the little vector here with the magnetic field stays the same, but we're not. We'll just take this for what it says. It says that the z component doesn't change with time, the average. So that's the first thing we discover. Now, to go beyond this, we have to know what the commutation relations are of the sigmas. So let's work them out. I think we have enough time. Let's work out the commutation relations of the sigmas, all pairs of them, and see what we get, and then plug it into here. I'm going to start with sigma x, sigma z, but instead I'm going to do it the opposite way. I'm going to calculate sigma z, sigma x. It's the same thing except with a minus sign when you interchange the two of them. So we'll have to remember, I'm calculating sigma z, sigma x. We'll have to remember to change the sign. Okay, so what is this? This is the product. Now, everybody remember what sigma z is as a matrix? We're going to do it now by matrices. I'm going to say the way to calculate this is to remember that sigma z and sigma x are matrices, or at least they have a matrix representation, and we just have to multiply the matrices. Sigma z, what was that? That was 1, 0, right? 1 minus 1. And what about sigma x? That's 0, 1, 1, 0. That's the first term in the commutator, sigma z times sigma x. And then the other term is just to put them in the opposite order. 0, 1, 1, 0 times 1, 0, 0 minus 1. No, we just take it, just the commutators of the matrices is what it comes down to. We could do it without the matrices, just by applying the operators to the vectors up and down, and we know enough to actually do that without actually using the matrices. But the matrices are a very convenient tool for manipulating operators. Operator product is the same as matrix product. Okay? So, does everybody know how to do a matrix product? I hope so. Let's do this one over here. The upper left-hand corner is the product of this row with this column, 1 times 0, 0 times 1, 0. The upper right corner is the product of this row with this column, 1 times 1, 0, 0, 1. The lower left corner is the product of this row with this column, that's minus 1. And then the last one is this column times this row, 0 times 1, and, 0 to this one, still 0. Okay, now let's do the other one over here. Minus 0 times 1, this one times this one, 0. This one times this one, minus 1. This one times this one, 1, 0. I think I missed a sign somewheres. Yeah, no, it's right, it's right. This is plus minus. Okay, so this, they just gave the same thing, but with a minus sign. Sorry. This minus this gave two terms which add. So the commutator is just equal to, the commutator itself is just equal to 0, 1, no, it's equal to twice minus 1, 0. Now, do you recognize this thing over here? If I put an I over here and an I over here, you might recognize it as being related to sigma y. Let me write down sigma y. Sigma y is equal to minus I, 0, 0. And what happens if I multiply sigma I by I? I times minus I is 1, and I times I is minus 1. So what this is it's just twice I sigma y. 2I sigma y. That's kind of neat. It's closing up on itself. Commutators of sigmas with sigmas are sigmas. That's good, because it's going to allow me to write equations for the time derivatives of sigmas, which are just going to be sigmas again. Okay, so let's see what we have. We have commutator sigma z with sigma x is equal to twice I sigma y. And now I'll write down the rest of them. Incidentally, as I said, if you want to get the opposite order, you just change the sign. Sigma z, sigma x with sigma y is equal to 2I sigma z. And zxy, sigma y, xyz, sigma z is equal to 2I sigma x. These are the three commutations. Do these remind you of anything? Do you remember the Poisson brackets of angular momentum? The Poisson brackets of angular momentum were Lz Lx equals Ly, Lx Ly is equal to Lz, and Ly Lz is equal to Lx. So apart from a factor of 2I, remember there is an I in the connection between Poisson brackets and commutators. These are essentially, apart from a factor of 2, which we can absorb, they're essentially angular momentum Poisson brackets. There's an important clue there for the meaning of angular momentum, but we're not going to dwell on it for the moment. These are the commutation relations of the components of the spin, and they just give back the components of the spin again, with this funny ordering, z, x, y, x, y, z, y, z, x. They're just permuted cyclically. Okay, so let's go over to here now. This now becomes minus I omega over 2. And now what's the commutator of sigma x with sigma z? It's minus 2I sigma y. So we get another minus 2I sigma y. The 2's cancel. That was the reason that I put a 2 in the denominator here in the first place, because I knew it was going to cancel. So let's cancel the 2. And we have minus I times minus I, which is minus 1. So what we get is minus omega sigma y. Notice that the I went away. The I went away. I was worried about it about a half an hour ago, that, oh my goodness, time derivatives of real things are going to get imaginary. But they didn't. They didn't because the commutators themselves had imaginary coefficients. And that's general. That's general. Okay. So there we are. We have sigma x dot is equal to minus omega sigma y. And sigma y dot, here we have the relationship for sigma y, and it involves twice sigma x. The correct relationship, if we work it out, is that this is equal to plus omega sigma x. Okay, so sigma z dot is 0, but what's happening to sigma x and sigma y? Can you see what's happening to sigma x and sigma y? Do you recognize these equations? These are the equations for a thing moving in circular motion, right? What's happening is simple. In the sense of expectation values are real numbers, and in the sense of expectation values, the spin vector is precessing around the z-axis. It's precessing around the z-axis. Sigma x dot is minus omega sigma y dot is plus omega sigma x. This is the same kind of formula that we discovered in classical mechanics when we talked about a rotor. Do you remember the rotor? And we also put the rotor in a magnetic field. The angular momentum executed exactly the same. And it's also the gyroscope precession. It's basically gyroscopic precession. A spin, a quantum mechanical spin, in the sense of expectation values, it doesn't make any sense to say that the quantum mechanical operators themselves precess. That doesn't mean anything. The quantum mechanical operators are just these matrices. They don't do anything. But because the state vectors change with time, the expectation values, or the average values of the spin, execute a motion which is basically the same as a classical rotor precessing in a magnetic field. Okay? So we have now solved the problem of a spin in a magnetic field. We've solved the hardest possible problem associated with a single spin. There is no Hamiltonian which is more complicated than this for the single spin. It's the most general. Of course, you could put the magnetic field in the x direction. All right, there's a little. Yes, you can solve a harder problem. You could put the spin along some peculiar axis. But what you would find after you work the whole thing out is that it would just precess around the peculiar axis of the magnetic field. Same thing. You just rotate it so that the magnetic field is pointing in a different direction.
Excuse me, any hints on why that?
What's that?
Any hints on why that's the correct value for the Hamiltonian?
There really aren't very many operators. Okay, so here's a general, you can work this out yourself. This is not hard to prove. The most general Hermitian operator in 2 dimensions is a linear combination of the unit operator, sigma x, sigma y, and sigma z. The most general Hermitian operator is a linear combination of these. Putting a unit operator into a Hamiltonian, that's like adding a constant to the energy. Unit operators commute with everything. So putting a unit operator in is not interesting. It does nothing. So we get rid of this. The next possibility is a general combination, linear combination, add them up, of a coefficient times sigma x, another coefficient times sigma y, and another coefficient times sigma z. That just corresponds to putting the magnetic field at some angle. It's just the simple case where we only took one of these is the magnetic field along the z-axis. If we took a general linear combination, let's say n sub x sigma x plus n sub y sigma y plus n sub z sigma z, this would just correspond to the component of the spin along the n-axis. And you would do exactly the same calculation, except you might work instead in the basis of eigenvectors of sigma dot n. So it really is the most general Hamiltonian that you can write down. And that's just because a two-dimensional space is so simple. There just aren't very many independent operators in it. There just is nothing else.
Can you comment on the relation between the two-dimensional space is the space of states, but we're sort of thinking in 3 dimensions here in terms of precession.
Right. But we worked, yeah. But remember, for every direction that you can think of, there is a state for which that component of the spin is definite. But that's secondary here. We're not, that didn't play very much of a role here. We just follow the rules. And, but yes, I mean, there are two things going on here. And this is a good place to focus on those two things. There are the 3 vectors, the vectors in real space. Those are the components of the averages of sigma. And there's the two-dimensional space of states, and they're quite different things, although they are related. Yeah.
Does omega represent some property of the magnetic field itself?
It's proposed. Omega is basically the product of the magnetic field times the magnetic moment of the little spin. Right. I don't know, there may be a 2, I have to remember, but no, I don't think there is. Yeah, there is a 2. Yeah. Omega over 2 is the product of the magnetic moment with the magnetic field.
Our original technique for creating sigma z was to put it in a magnetic field and have a photon go.
That was last year. Right. You're right. Right.
So, I mean, if we pursued this and coupled it to a field, we would see that thing.
Yeah. Right. If we couple the spin, now forget the precession. If we couple the spin to the magnetic field, then there will be 2 energy states. For example, if the magnetic field is along the z-axis, then the energy of the up state and the down state will be different. They'll differ by amount omega. Up will have energy omega over 2, down will have energy minus omega over 2, and there will be an energy difference of omega. All right, so one of them has higher energy, one of them has lower energy. What happens to a real spin if you wait long enough, if you put it in a magnetic field? The answer is eventually the higher energy state will emit a photon, and what will be the energy of the photon? Omega. Just a difference between the upper energy and the lower energy, and in the process of emitting the photon, it will flip. So these things are all certainly connected. But all right, we've solved a real, genuine quantum mechanics problem. Yeah.
So why is B not treated as an operator?
What's that?
Why is the magnetic field not treated as an operator?
Okay.
Its value is all 1 into omega.
If you were to think of the magnet as part of the quantum mechanical system, whenever you're facing the problem of a real quantum system which is being in interaction with a heavy system, with a system like a heavy magnet or some other kind of detector, an almost classical system, you don't bother trying to think of the heavy system quantum mechanically. You just say it has some parameter. Now that has to be justified. This is not obvious to justify. Why don't we have to think of the magnet as part of the quantum mechanical system? That's another way of asking the same question. And the answer is that it's so big and it's so heavy that it doesn't fluctuate much. But eventually we'll want to address that problem. For the moment, we just think of the magnet as part of a heavy apparatus which is sort of fixed and it's there, and nothing that electron can do is going to cause that magnetic field to change. It's just stuck there, and we get to think of it deterministically. When do we get to think about a thing deterministically? We get to think about a thing deterministically when it's so heavy and so many degrees of freedom that when we calculate the quantum mechanics of it, we find that the fluctuations are really small. But that has not been established yet. So far, we've divided the world into the quantum and the apparatuses, the heavy apparatuses, which we don't have to deal with quantum mechanically. That, of course, has to be a temporary thing. Real apparatuses are made out of the same thing as the systems we study. And so at some point we have to come back and say, what was the justification for saying the apparatus was allowed to be considered just classically, you just point it in some direction and that's the way it is, and the spin dealt with quantum mechanically. We will have to come back and answer that. But you know, my usual statement at this point is not tonight.
Sigma X dot and sigma Y dot, those are average values.
Yes, yes, that's what.
Yeah, so if you do the experiment a zillion times, will it fail on the way?
What?
Suppose you do
Yeah.
the experiment
Yeah.
zillions of times, will it occasionally fail in a predictable manner?
No, in an unpredictable manner.
Yes, right.
Right. Yes, the answer is yes. It will occasionally fail. But that has little to do with quantum mechanics. Well, it has to do with quantum mechanics, but it has to do with the use of statistics and probability. Why does probability work? We make a basic postulate, and that's that if you do an experiment over enough times, the average value that you get in the laboratory will agree to within small precision with the mathematical averages that you calculate from a probability distribution. I am not going to try to justify that. The reason is I don't know why it's true. And why does probability work? Why, if I tell you you flip a coin 1,000 times, does it come up heads 500 times? No. There's no such prediction. Certainly not, I mean, it might come up 500 times heads, but there's no prediction that says it does. Will it come up 500 times plus or minus square root of 1,000, plus or minus 30? That's the margin of error. Not every time, no, so there's no such prediction. What can you say? You can say it will probably come up, you know, we get into this cycle. How about if I do it 1,000,000 times? Will it certainly come up 500,000 plus or minus square root of n? No. No matter how many times you do it, there is no hard and fast prediction from probability that any particular thing will happen. Why does it work? Jesus, it beats me. But it does. Many, you know, I'm not the only one who's been puzzled by this. I mean, you know, I used to like to joke that this is probably the reason that Einstein didn't like quantum mechanics.
You started off giving different components to sigma X, Y, and Z.
Say it again?
On the far left, you assign different components to X, Y, and Z.
Yeah.
Set it in an original direction. That's reflected in your makeup, right?
Now, we could have done the same calculation by, instead of putting sigma z here, putting this sigma dot n. Sigma dot n is the matrix in the notation that we've been using up till now, where the sigma matrices are the things I wrote down. It would be the matrix n is a unit vector. N sub z minus n sub z, nx minus I ny, and nx plus I ny. It's just taking the components of n and multiplying them with the corresponding components of sigma. And then you could start with this and say, this is the I'll put an omega over 2. And take this to be the Hamiltonian. And then recalculate what happens to the different components of spin. Well, the component of spin along the n-axis, what would we do then? Then we would have to calculate commutators of the various components of the spin with sigma dot n. Sigma dot n. What about the component along the n-axis? What happens to it? The commutator is 0, right? Sigma dot n commutes with sigma dot n. So we would find out that the component of the spin along the n-axis would be the thing that doesn't change. How about the components of spin perpendicular to that axis? We could work that out. And we would discover that the spin precesses about the n-axis. That's a good exercise to try to do. I mean,
I was asking whether the omega reflected the orientation. You moved it from the omega into the dot n.
if you wanted to say it again,
I was asking whether the omega, the value of omega reflected the orientation of the spin, and you moved it from the omega into the dot n.
no, the omega is just a number.
Because if you put the dot n there, if you hadn't put the dot n there, the omega would have reflected the orientation in your original.
By orientation, you mean plus or minus 1? Or you mean direction? No. Omega doesn't have to do with the direction. Omega is just the magnitude of the magnetic field. Magnitude of the magnetic field times the magnitude of the magnetic moment. No, not dotted. They're just numbers. They're numbers. The dot product is between sigma and n. Omega is just a spectator. It's just a number. It's just a number. Oh, you can if you like. You could take this omega and put it with the n if you wanted to.
That was my point, that the H is variable. Whether you think of it as the omega or the dot n, it still depends upon the orientation of the spin.
What depends on the orientation of the spin?
The energy eigenvalue, the H.
One of us is confused. I'm not sure which.
The confusion is that when you had sigma z up there, that implies the magnetic field's in the z direction.
Here the magnetic field was in the z direction.
And that's the omega z you had before, right?
Omega z. Where did I have omega z?
You had h equals omega over 2, sorry, sigma z.
Sigma z, yes, sigma z.
Where is the spatial vector of the spin represented?
Omega dot n means dot product.
I can't remember which book I read it in, but they said whenever you're talking spin, you're really not talking 1/2, you're talking 1/2 pi. Is that?
Yeah, I think I read that. I read that too. I think it was in Newt Gingrich's last book. I don't know. Look, sigma dot n stands for sigma x nx plus sigma y ny plus sigma z nz, exactly as if sigma was a classical vector. But, of course, it's not. It's just a collection of 3 matrices. So this stands for a matrix. This stands for a single matrix, which happens to be the sum of 3 particular matrices. But that's the definition of sigma dot n, if you like. These are the components of n, and they determine the direction of the magnetic field. We multiply that by omega over 2, which is just a number. Just a number. Nothing more complicated than a number. And this is what sigma dot n means. If the magnetic field is along the z-axis, then the only component of n, which is non-zero, would be n sub z. Okay? If the magnetic field was along the z-axis, then we would say only n sub z. If you like, would you like me to write down the relationship between n and the magnetic field? The relationship between n and the magnetic field is that the magnetic field vector is equal to the magnitude of the magnetic field times the unit vector n. Okay? The magnetic field as a vector is the magnitude of the magnetic field times the vector n, and that stands for a magnetic field that's pointing along the n-axis with magnitude b. Once we know that, then we can basically identify the magnetic field with n apart from a numerical coefficient. Numerical coefficient is buried in omega here. Once we know that, we can write this as the spin dotted into B. So I'm not sure what the questions are. There's something which is bothering some of you. I'm not sure what it is.
When you flip it, you get a frequency. Is that frequency always the same, or does it depend on the spin orientation?
It depends on the magnitude of the magnetic field, nothing more.
Is it dependent on the dot end?
You're talking about the frequency of the photon? Yeah. No, the frequency of the photon is always just the difference of the energy of the upper energy level and the lower energy level, and it is always just omega. Doesn't depend on the, right. If you take sigma dot n and you ask what its eigenvalues are, the eigenvalues don't depend on n. They're plus and minus 1 in any direction. No, just the eigenvalues here. Let's write out sigma dot n. All right, here's an exercise for you. It should be done. Sigma dot n is n sub z times sigma sub z. That's nz minus nz plus nx times sigma x. That's that minus or ny sigma y. That's n dot sigma. Question, what are the eigenvalues of this matrix? Somebody's worked them out. I know that somebody in this room has worked them out. Who was it? The eigenvalues of this matrix here for any n's, as long as they're unit vectors, if n is the components of a unit vector, in other words, nx squared plus ny squared plus nz squared is equal to 1, you will find that the eigenvalues of this matrix are always plus or minus 1. This is simply the statement that no matter what direction you point your detector, your apparatus, when the apparatus acts, it gives you plus or minus 1. Okay? So whatever direction you take here, the eigenvalues of this matrix are plus and minus 1. If you know a little bit about matrices, for those who know a little bit about matrices, let's prove it. The trace of a matrix is the sum of its eigenvalues. The trace means the sum of the diagonal elements. All right? First step. There are two eigenvalues. Let's call them lambda 1 and lambda 2. And the trace of the matrix is 0, this one plus this one. And that tells us that lambda 1 plus lambda 2 is 0, or lambda 1 is equal to minus lambda 2. So there are two eigenvalues, and they're equal and opposite. What about the determinant of the matrix? It's the product of the eigenvalues. So we now know they come in equal and opposite pairs. What's the product? What's the determinant? The determinant of this matrix is equal to minus nz squared, this times this, minus this times this, and that's minus nx squared minus ny squared, right? Nx plusiny times nx minus ny is nx squared plus ny squared. Here it is. And what is nx squared plus ny squared plus nz squared? 1. So the determinant, which is the product of the eigenvalues, is equal to minus 1. There's only one solution. Lambda 1 plus lambda 2 is equal to 0. That says lambda 1 is equal to minus lambda 2, and the product is equal to minus 1. There's only one such pair. It's plus 1 and minus 1. So all such matrices of this form have eigenvalues which are plus or minus 1. And therefore, the energy levels are always plus or minus omega over 2. One of them plus omega over 2, the other minus omega over 2. And when you flip from one to another, you get omega worth of energy. Right. So it doesn't matter which way things are pointing in. Yeah. I think it's time to go, but.
If an electron photon is prepared, let's say, in the x direction.
Yeah.
And you put it in a magnetic field that is in the z direction. Let it recess for a while, and then suddenly it aligns in the z direction.
Yeah. That's right. In studying, yes, I should have said, in studying the precession here, we've ignored the possibility that it can radiate a photon. Now, the probability to radiate a photon per unit time can be pretty small. Can be very, very small. In particular, if the energy differences are very small, as they would be in an ordinary magnetic field, it will precess many, many times before it emits a photon. So,
My question is, if it does emit a photon, since it's not exactly flipping, it's only going 90 degrees.
going from up to down.
Okay.
Remember, the two eigenvectors, up and down, or left and right, or in and out, correspond to opposite orientations of the spin. Even though the state vectors are orthogonal, the directions in space are 180 degrees apart.
So his imaginary situation, that electron is not going to suddenly do something other than what it was doing or orthogonal to what it was doing. Right? It won't suddenly do something
okay.
different.
There's a probability for the electron to decay and emit a photon. And that probability per unit time is typically small. So you could be unlucky, and after a quarter of a revolution, it might emit its photon. But that's extremely unlikely. You can estimate how many. Am I answering your question? I'm not sure.
No, it would be either in the direction it was going or flip opposite. It won't suddenly go to some other weird angle, like from X to Y to Z.
I think the question is that since it's not, it feels like the electron, as you compared it, it's not perpendicular to the magnetic field. It only goes halfway.
No. It's in a superposition of being up and down. It's one of the two of those. It's only the average, which is sort of in a cattywampus direction. It's in a superposition of being up and down. If it's down, and down is the lower energy state, it won't radiate. If it's up, it will radiate. So if you put the electron in some other direction, there will be some probability for it to radiate and a probability for it not to radiate. The probability for it to radiate is the probability that it was up. Yeah. Very confusing. Very confusing. All right. Okay, now I see what was bothering you. If the magnetic field is that way, and the spin is aligned that way, you might have thought that when it jumps, you only emit half the energy of a photon, half the energy. No. What's correct is that the probability for it to emit a photon is 1/2. Why? Because there's half a probability that this is actually down and half a probability that it's up if you were to measure the upness and downness of it. So that means the average energy that it emits is half, but it either emits omega or it doesn't emit at all. Good.
For more, please visit us at stanford.edu.